Okay, so like I said, we will be mostly interested in rolling without slipping, right? So
Yeah.
on a horizontal ground, there is, I mean, if you look at the textbooks, I think in most textbooks, this will be used. I think even in H.C. Verma, Resnick and Halliday. Okay, so this is a nice idea. Again, treat it as a horizontal. Okay, so it looks like inclined, but treat it as horizontal. Maybe I'll just try to put it horizontal. Okay. So here I can look at this, let's say disk again. Okay, so you can take it as a disk. Suppose if I take, let's say the center, okay, and take, let's say 2 points. Okay, so one at the bottommost point, the one which is touching the ground, and the topmost point. Okay, now the points, the center point is fixed. Okay, as the disk rolls forward, I think the points that are touching the ground will vary. So this B, okay, the points that are touching the ground, I'm calling them B. Okay, so it's obviously different points. Okay, so here, when we say that, suppose this disk, if it only translates, okay, so if it only translates, okay, so the disk has some center of mass velocity, right? And can I say that every particle of the disk will have the same velocity if it only translates? Okay, so suppose the center of mass of the disk, if we say that the velocity is velocity of center of mass, then the topmost point, okay, so at an instant, whatever particle is on the top, if I take its velocity, let's say Vt, its magnitude will be Vcm. And the bottommost point, it will be in the forward direction. So that Vb, the velocity of the bottommost point, is also Vcm. You get this?
Yeah.
Now, if the disk rotates only rotates about center of mass axis, let's say, if it just rotates, in that case, the center is not going anywhere. Okay, so center is not going anywhere. We can say that this Vc, earlier it was Vcm if it only translates, but now it is only rotating. So this is 0. Point is not going anywhere. Now, if I take a clockwise rotation, okay, with an angular velocity omega, the topmost particle will have tangential velocity. Okay, so the topmost point V sub t, capital T, will have tangential velocity. I'm using small letter t for tangential velocity, which is, if r is the radius of the disk, that would be r omega. The bottommost point will have tangential velocity to the left. Okay, so spinning, right? It's spinning in the clockwise sense. So the bottommost point will have tangential velocity to the left, which is r omega. Now, if I combine these two, okay, the translation as well as rotation, if I combine them, then I have rolling. You get what I'm saying? Okay, so if I combine both, so what we are saying is, now the center of mass will have this VCM, Okay, now if I look at the topmost point, whatever particle is at the top, it will have two velocities. Okay, so one is because of the center of mass, the other is because of the tangential velocity. So now the topmost point will have VCM plus the tangential velocity, sub t, small t, which is VCM plus R omega. Do you get what I'm saying? The bottommost point will have VCM to the right, but the tangential velocity is to the left. So if I take the bottommost particle, whatever particle is touching the ground, let's say if I take right side as positive, it will be VCM minus VT. Are you getting this? So now this, let's say we can write it as VCM minus R omega. Now, do we know that, sorry, my question was, if the points that are touching the ground, if they don't slip, okay, so we are saying rolling without slipping, right? So if they don't slip, that means, can I say the velocity of the points that are touching the ground should be 0? Okay, so let me repeat what I just said. The points which are touching the ground, if we say that we are only interested in a type of motion where rolling is happening but slipping is not taking place. Okay, the points which are touching the ground are not slipping. So that means if I take this point B, its velocity should be 0.
Yeah.
So if its velocity is 0, what we are saying is this VCM must be equal to R omega. You understand this? So when we looked at that example of painting the periphery of the disc, we put purple paint, right?
It's breaking again.
Okay, this is what I was saying. When we looked at that purple paint put on the periphery of the disc, we said for rolling without slipping, the length of the paint on the road was equal to 2 pi r, right? So if this happened in time t, okay. Okay, so this is what I was saying. When we looked at the situation where we put purple paint on the periphery of the disc, we said the length of the paint on the road was equal to 2 pi r. Now, when we allowed for one rotation, if t is the time taken for one rotation, okay, so if I take t is the time taken for one rotation, then I can divide this by, let's say, length over time, and then this is 2 pi over t r. So the left hand side, I can say this is velocity of center of mass. Right hand side, this 2 pi by t is like covering 2 pi radians in time period t. So that is omega r. You understand? So it's the same thing. But you have to understand one very important thing. The point that is touching the ground, okay, so the point that is touching the ground will have tangential velocity to the left and the center of mass velocity to the right. So that means the tangential velocity and the center of mass velocity, they should point in the opposite directions and they should have the same magnitude. Then I can say that the points that are touching the ground will have zero velocity, no velocity. So that's rolling without slipping. Okay. But if you look at the topmost point, the velocity gets added up.
Yeah.
Okay, now because we are saying in magnitude, magnitude wise, because VCM is equal to R omega, I can say that the topmost point will have twice the velocity of the center of the disk. Okay, so this is something that you should keep in mind.
Okay.
Okay. Now, what we will do is, let us understand there are two types of rolling without slipping. And then this rolling without slipping, they also call this pure rolling. Okay, so rolling without slipping is known as pure rolling. Now, this pure rolling can be of two types. One, the velocity of the center of mass is constant. The other, velocity of center of mass is changing. Okay, now when the velocity of center of mass is constant, this is called uniform rolling or uniform pure rolling. Okay, so uniform pure rolling. Now, when you have velocity of center of mass is changing, then you have accelerated pure rolling. So because we have acceleration, we can take one more step here. So we're saying the velocity of center of mass must be magnitude wise is equal to the tangential velocity. So if you take a time derivative, the acceleration of the center of mass must be equal to the magnitude of tangential acceleration.
Mm.
Okay, so this tangential acceleration is provided by the torque acting on the object.
Okay.
Okay, so now let's say talk about uniform pure rolling for a while. Okay, so let's take. I'm still, let's say, looking at this disk example.
Mm.
Okay. Now here, the moment the center of mass has certain velocity. Okay, and the disk has angular velocity omega about the center, and if r is the radius, if they match. Okay, now there is no need for any forces. I mean, if this situation is generated, okay, so you have velocity of center of mass, and then you also have angular velocity about the center of mass axis on a horizontal road. Okay, even if there is, let's say, friction, or even if it is smooth, in both cases. Okay, so no forces act on the disk. Look, when I say no forces act on the disk, no unbalanced forces act on the disk. Mg and normal are anyway there. The gravitational force and the normal force, they are anyway present. No unbalanced forces exist. Because if horizontally, if you have forces, then what will happen? If there is a force to the right, the velocity of center of mass will increase.
Yeah.
Now, if there is a force to the right, then you will have a counterclockwise torque. Then you will have counterclockwise angular acceleration.
Yeah.
Then angular velocity will go down. You understand?
Okay.
So now that cannot happen, right? If VCM increases, then angular velocity goes down, then the VCM will not be equal to r omega. So then it will no longer be pure rolling. Now, suppose instead of taking a force to the right, if I imagine a force to the left, then what will happen? VCM will go down. and omega will increase because there will be clockwise torque. Okay, so if you
Okay.
imagine there is a force, let's say this is my disk. Right now, VCM is R omega, but suddenly there's a force that gets applied to the left. I'm not saying that this is friction force, let's say some force. Then what will happen? VCM will go down. There will be angular acceleration in the clockwise sense. So omega goes up, right?
Yeah.
So now again, this balance will be disturbed.
Yeah.
Okay, so then it is not pure rolling. So on a horizontal ground for uniform pure rolling, just keep this in mind. Even whether the surface is rough or not, there is no unbalanced force that is acting on the disk. Here we are just taking disk as an example. It could be any round object.
Okay.
Okay. Okay. Now, some of the common type of problems involving rolling on a horizontal surface, we will try to, let's say, work on them. Okay. One particular type is like you are giving initially only center of mass velocity, but there is no rotation on a rough surface. What will happen is soon the disk will start rotating.
But it will not move.
It will be moving forward. It will also rotate. So it will kind of attain that state of rolling without slipping.
Okay.
Okay, so I'll explain that situation. Okay. Suppose I take a disk. Right now, only center of mass velocity is given. So let's call this as V naught. Okay, so omega is absent. But we are saying that this is a rough surface. Now, for our discussion, we are saying this is a disk, uniform disk. Okay, so maybe mass m and the radius is r. Now, in this case, what will happen if you give only center of mass velocity v naught? In the beginning, every particle of the disk will have that velocity to the right. So even the points which are touching the ground will have that velocity to the right. Right? So now because of the surface being rough, the surface will apply a friction force to the left. You understand this?
Yeah.
Okay. Now this friction force, what it does is, it will reduce the velocity of center of mass. And then it provides an angular acceleration which will start giving angular velocity.
Yeah.
Okay. So initially, okay, so let's say if I take this situation as t equal to 0, initially, only velocity of center of mass is there, which is v naught. The tangential velocity is absent because omega is not there. Omega is 0. So clearly we can say, if I consider the point of contact, okay, for the point of contact, the velocity of center of mass is clearly greater than r omega because omega is anyway 0. Now, what do we want to do? We want to create a balance here. VCM should be equal to r omega. So the VCM is greater, so I have to bring this down. And then I have to slowly increase omega from 0. You understand these arrows?
Yeah.
Now, who is doing that job? The kinetic friction
Friction.
force is going to do the job. Because friction is going to act to the left, it is going to reduce the velocity of center of mass and then increase the angular velocity, right? Okay, now how do I calculate the kinetic friction? We are assuming that the coefficient of friction is mu k, right? Now, if I use, let's say net force is equal to mass into acceleration. the Newton's second law for translation, and then I take right side as positive. The friction force is to the left. Okay, so I have minus Fk is equal to mass into acceleration of center of mass, right? So we know that friction force, I can get it by friction coefficient into normal, which is mu mg. I think this you should be okay.
Yeah.
So the acceleration of center of mass is minus mu kg. So that means the acceleration of center of mass is acting to the left,
Opposite.
opposite. Then whenever we take right side as positive, because we want the tangential velocity of the points that are touching the ground towards the other direction, we take clockwise as positive. So keep this in mind, sign convention. Okay, if right side is positive, we are looking at rolling without slipping. That is our ideal situation. So you want to take clockwise as positive. It doesn't matter, but just a convention. Now, about center of mass axis, I will apply net torque is equal to I alpha. Okay, so clockwise torque is provided by friction force. What is the magnitude of friction force? It is radius in perpendicular distance, which is radius, into the force. The angle between them is anyway 90. So Fk. That is equal to I alpha. You're okay? Now, what is Fk? We already have it here. Mu k mg. So we will substitute here. Mu k mg. And then this is equal to I. For disk, it is mr square by 2.
mr square by 2.
And then alpha. Now, what do we get alpha as? Alpha is 2 mu k g by r. You're okay here so far? So we have ACM, we have alpha. Now, after some time, if we are saying that this disk is going to roll without slipping, let's say at time t. Okay, so at time t, if the disk rolls without slipping, so the center has some velocity v, and it is going to spin with angular velocity omega. The points which are touching the ground will have VCM to the right and V tangential to the left, and then both are equal in magnitude. Okay, so I can use this condition, right? So if I use this condition, VCM is equal to VT. Now, if I look at the linear acceleration is constant.
Yeah.
Angular acceleration is also constant. So now you have these simple kinematic equations. V is equal to U plus AT, and then omega is equal to omega naught plus alpha t. We can use them. So for the left hand side, if I use V is equal to U plus AT, initially I have V naught plus the acceleration is in the opposite direction, which is minus mu kg, and then I multiply by time. The right hand side, I have tangential velocity, which is r omega. Okay, omega, how can I write? Initial omega is 0. Final omega is plus alpha t. We are using these two equations. V is equal to U plus AT. And the right hand side in the bracket, I'm using omega is equal to initial omega naught plus alpha t. Alpha is 2 mu kg by r into t. You understand this? Now here, I hope you understand this minus sign, why I have put minus here on the left hand side for acceleration. So if I solve this, I'll get time. What is the time? I think mu kgt will go to the other side, r will disappear. So time is...
Shouldn't it be t square over here?
No. Why? This is alpha into t, right? Omega is equal to omega naught plus alpha.
Oh, sorry. Yeah.
The basic one, the basic equation.
Yeah.
Okay, so from here, if I solve, the time that we get is V naught by 3 mu kg. Sorry, 3 mu kg. You understand this?
Hmm.
So that means this is one, let's say they might look for these time. Okay, they might say that, okay, the round object is given only center of mass velocity on a rough horizontal road. So the surface will end up providing, let's say, linear acceleration in the opposite direction, which would bring down the center of mass velocity, but it will provide angular acceleration, which will help the disk gain angular velocity. Slowly, it will attain pure rolling. Now, if they ask you a question, okay, in what time the pure rolling is attained?
3 by
Okay, so you can use
V naught.
yeah, you can use whatever we have done to get that. Understand?
Okay.
Now, another question that they may ask is, okay, what is the velocity once it starts rolling without slip? So in that case, I can use this time in the left hand side. So if you see here, the velocity of center of mass once it starts rolling without slipping will be VCM is equal to this V naught minus mu kgt. So what is mu kgt? It is V naught by 3. So it will be V naught minus V naught by 3. I will end up having 2 V naught by 3. Are you okay here?
Yeah.
Okay, so these are the typical, well, this is one typical format of questions which are used to test the understanding of rolling motion. Okay. Okay, so one last thing that you need to, let's say, be aware is, once it starts rolling without slipping, the friction force will switch off to 0.
Okay.
Because again, if friction force is there, then what will happen? It will be either to the right or to the left, right? Depending on the slipping direction. Then it will again cause imbalance. That points of contact, the center of mass velocity and the tangential velocity's magnitude will not be same. Okay, so again, maybe conceptually they might ask, let's say if a round object is rolling without slipping on a horizontal ground, what is the magnitude of friction force? If such a question is asked, simply, what is the answer? What is the answer? If a round object is rolling without slipping on a horizontal ground, my velocity should not change. Angular velocity should not change. What is the magnitude of friction force?
0.
Very good, 0. You just keep that in mind. You understand? Okay, so here I'm taking a different scenario. We still have the disk. On a rough horizontal ground. So this time there is no center of mass velocity. Let's assume that I have given angular velocity omega in the clockwise sense. Now here, if I take these points of, let's say points on the periphery, because of this clockwise angular velocity, they're going to rub against the surface and then move to the left.
Yeah.
Yeah, if the surface is very smooth, then they will nicely slip to the left, and then the disk will spin at one place. Okay. Now, because the surface is rough, what is going to happen? Because these points are slipping to the left, the friction force is to the right this time. Okay. Now here again, if I think about it, at t equal to 0, the points which are touching the ground, okay, so they have only tangential velocity, which is r omega. And the center of mass velocity is 0. So we can say that the center of mass velocity is less than r omega because it is anyway 0. Now, what do we want? We want a scenario where the center of mass velocity is increased and then omega is brought down in this case. Now, who is going to do that job? Friction force. Now, again, since I'm taking the same object with mass m, radius r, can I skip the calculation of calculating friction value, which is mu k mg anyway?
Yeah.
This time, linear acceleration will be in which direction?
Right.
Right side, very good. So I think I can just take that this is mu kg, because if I write, it's the same thing. Now, angular acceleration will be in which direction?
Clockwise.
Friction is pointing in which direction? If you use right hand thumb rule, about center, alpha will be in which direction? So if you use right hand thumb rule, the four fingers go from the center to the point where the force is getting applied. And if you curl the fingers towards the force, thumb is pointing in which direction?
Inside.
It's pointing inside or outside?
Inside.
Are you using your right hand?
Yeah.
Your fingers should, four fingers should come from C to this point of contact.
Okay.
Let's say your four fingers should come like this, and then they curl towards the force vector.
Inwards. No?
See, don't look at the image, but if your four fingers are like coming from C to B, okay, let's say your little finger is going to touch the board, right? If your little finger is going to touch the board, your thumb is going to point outwards, right?
I'm supposed to do like this, not like this.
No. The four fingers should go from C to B.
Okay, I don't know.
You have to practice this right hand thumb rule. Okay, I'll explain. Okay, this is C, right?
Yeah.
And this is the point where force is getting applied. The force is getting applied in this direction. So this is your position vector, R vector. So your fingers should point in the direction of the position vector, and then they should curl towards force vector.
Okay.
Can you try that? So the thumb should point outwards.
So should it point towards me or away from me?
Towards you. Are they pointing towards you?
No.
See, you take fingers below C.
Oh, my fingertip should point this side.
Yes.
Okay,
your
yeah.
thumb should point towards you.
Okay, yeah.
So that means the fingers are curling in the counterclockwise sense. So you get angular acceleration in the counterclockwise sense.
Okay.
Okay. Now the angular acceleration, I think again we'll borrow from the previous discussion, which is 2 mu k g by r. Okay. So we are borrowing these two. Okay. So we are not trying to calculate this because it's the same calculation. Yeah. It's just that the directions are reversed. So I'm taking right side as positive and then clockwise direction as usual as positive. Okay. Here again, if I'm trying to get the time in which the pure rolling begins. Okay. So I want my VCM equal to R omega. Understand? So if I take this disk, once it starts rolling without slipping, so it will have some velocity, it'll have some omega. Now this time omega will be reduced. VCM will increase from 0. So if I use V is equal to U plus AT, there was no velocity, plus alpha A is to the right. So I'll write mu K G in T time this is happening, equal to R. Initially we had omega. Okay, omega naught is omega here. plus alpha, but alpha is in the other direction. So I'll have to take it with a minus sign, which is 2 mu k g by r into t. You follow this?
Hmm.
Now here, if you look at the time, here we get r omega by 3 mu kg. So we get, this is the time in which the pure rolling starts. Now, if you want velocity, I think we can find the velocity of center of mass. Velocity of center of mass will be, I can substitute here. Okay, if I substitute here mu kg t, I'll get r omega by 3. Are you able to follow this?
Yeah.
Okay.